Next up, we're looking for the Lewis structure of IF4. And so just a quick algorithm on how to find the Lewis structure. So first off, we want to determine our central atom. It will usually be the one that can make the most bonds. And so to figure out how many bonds an atom can make, you simply do the calculation of 8 minus the valence electrons, and that will give you the number of bonds it can make. And so let's go ahead and do that. If it's I, it's going to be 8 minus our valence electrons for I, and that is going to give us 7. So ideally it would make 1 bond, and the same thing for fluorine, it's going to make 1. So in this scenario, it's not clear which one is going to be our central atom, but the one that we have less of in the scenario is going to be our best central atom, because that just logically makes sense. And so our structure would look something like this. For our next step, we are going to want to logically arrange your atoms. So in this question, that is how we got the skeleton. So you just logically arrange atoms. And lastly, we want to account for all valence electrons in a manner that minimizes formal charge and places negative charge on the more electronegative atoms. And so if you go about doing that, let's count our valence electrons first. So it's IF4 minus. So our valence electrons are going to be 7 plus 7 by 4 plus 1. If we label that, that is I, F4 minus, and that is going to give us 35 plus 1, which is 36 electrons for us to account for. Okay, and then, so in our structure, let's go about making single bonds first and filling in any octets. Okay, and so fill in on the fluorine first. And then let's go about counting our electrons. So we have 6 by 4, because 6 on each of the fluorines, plus the 8 electrons that are in the bonds. And that is going to give us 24 plus 8, which is going to give us 32 electrons. We have 36 electrons, which means we're going to have a remaining 4 electrons. The best place to place them is going to be on our central atom. Let's go about doing that. And so that is going to give us a structure that looks like this. Okay, and then we can go about checking on our formal charges. For each of the fluorines, that is going to be 7 minus 6 minus 2 over 2. That's just 7 minus 7, giving us a 0. On the central atom, it is going to be 7 minus, we have 4 non-bonding electrons, minus 8 electrons that we have in each of them. And so that is going to be 7 minus 8, and that is going to give us minus 1. So the I in the center is what is responsible for the negative charge. And so our formal charges make sense, our valence electrons make sense, making this our final structure. Okay, next up, we are looking for the Lewis structure of ClF5. So let's go about doing that first. Let's count our valence electrons. 7 from the chlorine, 5 by 7 from the fluorine. And that is going to give us 35 plus 7, so 42 electrons to figure out. Let's go ahead and label that. Okay, and so if we start with just a structure like that as our skeleton, let's go about just labeling with one single bond on each and filling in each of the octets for the fluorines. Okay, and then let's double check all of our valence electrons have been accounted for. And so we have 6 by 5 plus 2 by 5. And that is going to give us, just one moment, 40 electrons. And so we have 2 left over, and it would be best to place those on our chlorine. Okay, and so now we want to double check on our formal charges on each of them, just to ensure everything is making sense. So on the fluorine, we are going to have 7 minus 6 minus 2 over 2, and that is going to give us 7 minus 7, which is 0. On the chlorine, we are going to have 7 minus 2 minus 10 over 2. Which is 7 minus 7, so again 0. So the formal charges make sense, valence electrons are all accounted for, and this structure is possible because chlorine is allowed for an expanded octet. So this is going to be our final Lewis structure. For our next part, we want to find out the molecular geometry before we go about finding the electron pair geometry. And so for our molecular geometry, let's find out how many electron pairs the central atom has around it. So it has 1, 2, 3, 4, 5 in bonding pairs, and an additional 1 pair that is a lone pair. And so it has a total of 6 pairs attached to it. And so if we pull up the VSEPR chart, we see that we have 6 pairs around it, so we're going to come to this row, but we have 1 lone pair. And so what this means is that our molecular geometry, so let's just write down a hybridization quickly. So it has 6 electron pairs, and so that is going to be sp3d2. And so if you just add up all of the powers, it should add to 6. So 1 plus 2 plus 3, and that's going to give us our 6. And so this means that the molecular geometry is going to be octahedral. But then our electron geometry is going to account for the fact that we have 1 lone pair, and so it's going to be square pyramidal. And so you can think of molecular geometry as you're ignoring the fact of whether it's a bonding pair or a lone pair. And so generally the shape would look like an octahedral shape, but then because it's a lone pair, because you have 1 lone pair, if you're only looking at the bonding pairs, that would look like a square pyramid with the 2 electrons on the bottom, as you can see here. And so these are our 2 answers. Molecular geometry is octahedral, electron geometry is square pyramidal. What that just means is that you have 1 lone pair here, and that's going to affect the other angles, making them a little under 90 degrees rather than the optimized 90 degrees in the octahedral shape, just because of the lack of symmetry in the electron repulsion. And so those are our 2 final answers.